Welcome to Chapter 5. In this chapter, we explore overfitting, underfitting, and generalization, the ideas that decide whether a model is genuinely useful or only looks good on paper. Machine learning models can fail in a very particular way. Two failure modes stand between us and good generalization, and learning to recognize both is what this chapter is about. By the end of this chapter, you should be able to explain what generalization means and why it is the true goal of machine learning, tell overfitting and underfitting apart, describe how model complexity relates to error, and explain the bias-variance trade-off in plain language. You should also be able to say why training error and test error can differ and what their gap reveals. Use validation data and cross-validation to choose complexity. Explain regularization and the difference between L1 and L2 penalties, and read validation and learning curves. This figure captures the whole story. As complexity rises, training error keeps falling, but validation error follows a U-shape. The sweet spot sits at the bottom of that U. To its left, we underfit, and to its right, we overfit. Let us pin down the central term. Generalization is a model's ability to perform well on new data it never saw during training. A model that generalizes has learned the underlying pattern, not the particular examples it happened to see. A model is only worth deploying if it generalizes. Everything in this chapter circles back to that single idea. Now, consider the warning sign. When training error is low, but test error is high, the model has learned the training set too closely and failed to capture anything that transfers to new cases. Here is a key point. Never judge a model by its training error alone. A perfect score on training data tells you nothing about the real world. The gap between training and test error is what reveals whether the model truly learned or merely memorized. Let us look at the first failure mode. Underfitting happens when a model is too simple to represent the true relationship, often because it is too simple for the pattern, important features are missing, training stopped too early, or its assumptions do not match the data. Underfitting can also come from regularization so strong that it crushes the signal along with the noise. There are a few clear signs that tell us it is happening. The telltale symptoms are high training error, high validation or test error, and poor performance even on the very data the model trained on. To cure underfitting, the recipe is simple in spirit. Give the model more room to learn. Concretely, switch to a more flexible model or add polynomial features, engineer or collect more informative features, reduce the regularization strength, and train longer when the model learns iteratively. Now, the opposite failure mode. Overfitting tends to strike when the model is too complex for the data available. The training set is small, irrelevant features distract it, the data is noisy, or an iterative model is trained for too long. You can spot overfitting by its fingerprints. Very low training error, much higher validation or test error, and a large gap between training and test performance. The remedies for overfitting pull in exactly the opposite direction from the cures for underfitting. Specifically, use a simpler model or constrain the one you have, collect more training data, remove irrelevant features, apply regularization, use cross-validation to choose settings honestly, and stop training early when validation error starts to climb. These two diagnoses fold into a single decision procedure. Compare training error against validation error, read off which failure mode the gap points to, and apply the matching remedy. This figure shows that procedure as a flowchart. When both errors are high, you are underfitting. When there is a wide gap between them, you are overfitting. Model complexity measures how flexible a model is, how intricate a pattern it can bend itself to fit. Too little complexity leads to underfitting. It shows up as the degree of a polynomial, the depth of a tree, the number of trees in an ensemble, or the number of neighbors k. It also appears as the number of layers and neurons in a neural network, which we meet in Chapter 14. Choosing these settings well is one of the central skills of the trade, and the rest of this chapter gives you the tools to do it. The bias-variance trade-off is the conceptual heart of this chapter, and a dartboard makes the distinction wonderfully vivid. In this figure, each red dot is the prediction of a model trained on a different sample, and the bullseye is the truth. Bias is how far the cluster of shots sits from the center, while variance is how scattered those shots are. Here is the key point. Underfitting is mostly a bias problem, overfitting is mostly a variance problem, and good generalization comes from balancing the two rather than eliminating either. That is why the best model is rarely the most complex one available. Regularization is one of the most practical tools for fighting overfitting. Many models train by minimizing a loss function, and regularization adds a penalty to that loss. The two workhorse penalties are L1 and L2. L1 regularization penalizes the sum of the absolute values of the coefficients, which tends to drive some of them all the way to zero and effectively select features. L2 regularization penalizes the sum of the squared coefficients, which shrinks them smoothly towards zero without forcing any of them to vanish. A validation curve answers a focused question. As we dial one hyperparameter up and down, how does performance change? It makes an abstract warning concrete that the most complex model is usually not the best one. A learning curve asks a different question. What happens as we feed the model more data? If both curves level off at a high error and stay close, the model is underfitting. If training error is low, but validation error stays well above it, the model is overfitting. A single train validation split has a weakness. The estimate depends on which points happen to land in the validation set. In k-fold cross-validation, we carve the data into k equal folds and rotate through them. One caution, it only estimates generalization to data from the same distribution. When the symptoms point to underfitting, that is, high error everywhere, and a model that cannot even master its training data, reach for the following moves. Use a more flexible model, add more informative features, reduce the regularization strength, improve feature engineering, train longer if the model has not converged, and choose a model whose structure fits the data. When the symptoms point to overfitting, that is, near-perfect training error and a large gap to test error, pull the other way, collect more data, use a simpler model, remove irrelevant features, apply regularization, and use cross-validation for model selection. There's more in the same vein. Use early stopping for iterative models, reduce model depth or complexity directly, and use data augmentation where it makes sense, a technique common in image work that we revisit in Chapter 21. Data leakage is one of the most embarrassing ways a project can fail because it makes a broken model look excellent right up until it ships. A subtler version comes from features that only become available too late to actually use. Here is the key point. Leakage gives you a model that aces the exam and fails on the job. Always split your data first, fit preprocessing only on the training portion, and ask of every feature whether its value would truly be available at the moment you need to predict. Let us make this concrete with code, because nothing makes the complexity trade-off stick like watching it happen. We start by generating data from a smooth curve and adding a little random noise so that we know exactly what pattern the model should recover and what is just noise it ought to ignore. This code creates that synthetic data set, splits it into training and test sets, and then fits polynomial models of increasing degree, recording the training error for each so we can watch how fit changes with complexity. Because the true relationship in this data is a cubic, we expect degree 3 to fit best, with lower degrees underfitting and much higher degrees overfitting the noise. Now let us see regularization at work on a real regression problem and confirm that a well-chosen penalty actually improves generalization. This code loads the California housing dataset, splits it, and then trains ridge regression at several penalty strengths, scaling the features first and reporting how well each model fits as the penalty grows. Here, the alpha value controls the L2 penalty. Larger values shrink the coefficients harder, trading a little fit on the training data for better behavior on new data. Consider this case study where the best training score turns out to be the wrong goal. A digital lending platform builds a model to predict loan default with data on tens of thousands of borrowers and dozens of variables, and reaches for a very complex model to squeeze out every point of accuracy. During development, the complex model looks superb, scoring almost perfectly on the historical data, yet it stumbles on real applicants. The fix is everything this chapter has argued for, and the lesson generalizes far beyond lending. The following code generates synthetic loan data and fits polynomial regression models of increasing degree, printing a table that shows train error falling while test error rises as the degree grows too large. This code builds the credit score to risk dataset, splits it, and loops over several polynomial degrees, fitting each model and computing its training and test error so the overfitting becomes visible in the numbers. The printed table shows train error decreasing steadily as the degree rises, while test error reaches a minimum around degree 1 or 3 and then climbs sharply, the signature of overfitting. This chapter put generalization at the center of machine learning. We tied its failures together through the bias variance trade-off. Underfitting is high bias, overfitting is high variance, and good generalization balances the two. To go further, look at introductory texts on the bias variance decomposition, the scikit-learn documentation on model selection and cross-validation, its guides to validation and learning curves, and applied resources on detecting and preventing data leakage. That brings us to the end of Chapter 5 on overfitting, underfitting, and the goal of generalization that ties them together.